Good afternoon, everyone. So for some of you might have seen most of these slides before, but for most of you this might be a new project altogether. So I'm from the University of Pretoria. My name is Lelanie Smith, and we run a small UAV group there, a engineering design group that we refer to as Team Arendt. Okay, so basically my presentation is going to be on how we came into existence, what we are actually doing, and what the idea is from an academic perspective, what we are doing. Okay, so just on the agenda, I'll give you a bit of introduction and background to the project, the team structure, how it works, the project objective, the concept of operations, the aircraft design. I won't go too much into the detail there, and just give you some information of where we are in terms of the project at the moment. Okay, so just to give you some background, and this is old news, I guess, for most of you. What happened was in 2014, we had a group of students from America that wanted to take part in a competition that they wanted to do in the Kruger National Park to provide a technological solution for rhino poaching. And so they contacted us and asked us if we wanted to be part of their collaboration. The American team, University of Colorado, would be the embedded systems group, and we would do parts of the aircraft and also advise them in terms of the local atmosphere, like the environment, the people that will need to work with the drone and technology, and so forth. So that's how the project started, but the competition actually fell flat on its face and it never happened. But from the beginning, we saw that the competition wouldn't actually give a platform to provide a solution for the poaching problem. And so in the end, what we did is we turned this into more of a research platform and for undergraduates and postgraduate students to interface and engage with a project where there is a real outcome at the end. So to go over to the team structure. So initially we set up the team from the University of Colorado. They started the group. And so they were the founders. We had a Kickstarter funding. So any funds and everything that we have, we got through the Kickstarter funding that we raised. They were in charge of doing the payload, the communication systems. We took charge of the concept of operations, like what we actually want to achieve with this aircraft, designing the fuselage, everything around that, landing, launching systems, and we will also be the center of integration. We had the University of Stuttgart, and they were going to do the wings and the empennage, so also parts of the aircraft. And then Metropolia University in Finland, and they would do a ground network system. Okay, so this worked fairly well at the beginning from the other universities because they all had students through coursework working on the project. But when we started, we only had volunteers helping us. We had no way to integrate this into a curriculum. Now, a student and a volunteer is quite a volatile thing. When you need them the most, they are nowhere, and when you don't want them, they are everywhere. So what we had to do after the first year of working in this project, we had to figure out how to actually use our curriculum to integrate the students and to integrate this program into what we wanted. Now, in academia, they always have these really big words to describe something that's actually quite normal. In your day-to-day experience in engineering, you'll find that you run multinational, multidisciplinary, vertically integrated projects. And so that's the academic name for what you do on a day-to-day basis. And basically what that meant is we're integrating between nations. We have the Germans, the Americans, the Finnish teams, and us. We have multidisciplinary, we have electronic, computer engineers, mechanical, aeronautical engineers, and some industrial engineers as well. Vertically integrated is quite a new concept in universities for some reason, but it's to work on projects together from second year all the way through to master level. And so what we did in the end in this quite complicated structure is we had a whole top-down system. So me being one of the staff members, I could run the project almost as a project manager, kind of from that point of view. We had a couple of master students, one on the electronic side, one on the mechanical side, to oversee bigger aspects of the project. And then we have final year design and research projects. So we tagged into that, and each lecturer usually has a couple of those students. So we would give them smaller parts of the bigger project. So one student, for example, would design the launch mechanism, one student would design the landing mechanism, one student would do the interface between the body and the wing. So they would have a small project that they become the manager of Below them, we then have third year and second year students, and we have courses at the University of Pretoria that we call like vacation work, holiday work. They have to do all kinds of things like manufacturing, small design packages. So we basically have students from second year coming into the project. They learn how to do composite manufacturing. They learn how to do things around the aircraft, maybe mission planners, how to fly and so forth. They can then go over into their third year doing small design tasks like how do we put the batteries in the aircraft, what housing do we need, and then they answer to the higher level students. So the whole project in the University of Pretoria side is run through almost 20 students and from second year all the way through master level. And then we interface with the international team. So we'd have, if there's someone on a wing type of project or the interface between the body and the wing, they'd be directly linked to the Stuttgart team, and they'll have interactions and Skype meetings and so forth. So it's quite a nice project. And what we found is there's a lot of scope for challenges and opportunities to fall out of this project that we don't formally address in the curriculum. So we can't really in curriculum formally address and test soft skills that students definitely need for industry, like communication would be a big thing, and now we're communicating beyond different nations and different disciplines. So it became quite a big challenge, and there were a lot of interesting crises that came out from the project that we had to manage. They get an idea of a systematic approach and their role within a bigger system. They understand that they're not only doing some small manufacturing task, but there's a larger thing at risk here. If their little pin is not manufactured exactly to the spec, the whole system stands still. And that gave them quite an interesting feel for how these projects typically would work. How to do student involvement and handing over of a project was quite a big thing. We had a couple of challenges of students not being able to communicate properly what they've done and what needs to be done. And that gives them an interesting challenge to really reflect on what they've done and how they need to carry over and what the next person will need to do. So there's a couple of things, also very interesting ideas in terms of the technical side coming out of these projects. So it really became a nice platform for students to engage and be part of a project that has a bigger outcome. So just in short, just to give you an idea of what we actually ended up doing. So we decided as a project objective to go away from a reactive response in terms of the drone and try for a proactive response, knowing that this is a quite difficult concept to follow. We decided, well, within the Kruger National Park, it doesn't make a lot of sense to go on permanent surveillance. So we came up with a concept where we would design something that will find the poachers before they even reach the rhinos. So that was the idea behind this. And in order to do this, we then said, well, within the space that we have, we probably will need like multiple points where we launch these drones from. And so we divided the Kruger Park into multiple segments. And these segments were divided in terms of how far our comm systems would be able to operate. So all of these red dots are 60-kilometer diameter. So we said we are designing a range drone to be able to reach up to 30 kilometers out and then go into a specific search pattern. From the search pattern, it will be able to find the poachers, follow them, and only send back locations. So the idea is to do onboard processing as we find the drone. So this is just a schematic to give you an idea of what the search pattern would look like. And again, in this project, because we had the novelty of designing without using anything off the shelf, and we do it specifically like that so the students have the opportunity of really looking at each small little phase, and we don't really get much off the shelf. So we look at things like we have a specific camera spec that we want to have. How high do we need to be for that camera to work ideally? What speed do we have to fly for that camera to work ideally? If we fly that low for the camera, how loud is the aircraft going to be? Will the poacher hear it? So all these kind of questions were part of the beginning process of developing different systems in this aircraft. So every single spec that we in the end came up with was specifically designed for what exactly we planned to do with this. And so in the end, the higher level design objectives were that it's a long range, not an endurance aircraft, a quick response vehicle. So as soon as there's a trigger in the environment, we will be able to go to the trigger point. Low noise to be able to fly without the poachers noticing us. Modular payload, as the sensors are changing so fast, we need to be able to upgrade the sensor system easily. onboard processing, and then, of course, the ideas in the end to do autonomous flight. Okay, so I see my 5-minute notice. Yes, so just a couple of points on the requirements. I'm not going to go in too much depth on this. We have a Facebook page and we have a very nice publication, as most academics have, on all the specs and all the technical information you'd ever need. So I'm just going to go through a couple of key points, like it's an 18-kilogram aircraft, 20 meters per second cruise speed, the range of 90 kilometers, wingspan of 4.2. We have the prototype drone displayed next to our stand, so you're welcome to go look at that. Just a couple of the systems that we have designed. We have the gimbal system, which we've tested statically. We have the landing skid system, which we are testing in July, the landing gear. And then we have this central spine design that you'll see. And also, if you go look at the drone, where all the structural forces run through the central spine. In this way, we are also able to then quickly click on and click off any aerodynamic shell. Because a lot of the work research side in the University of Pretoria is based on configurations, we want this drone to be able to test different configurations. So we want to change the fuselage, change the wings easily without disrupting all the embedded systems and the payload systems. Then we have fairly standard embedded system. We have the payload processors that sit in the nose. We have the autopilot. We use a normal Pixhawk, and we have the telemetry and the propulsion systems all integrated. So this is fairly standard, and a lot of information in the paper on this. And so just to finish off, to give you an idea of what we've actually done physically. So the first year, end of 2014, we had the German team come out with the wing and the empennage, and we did gliding tests. We did some structural tests with John Monk's team at the CSIR to see if the wing will actually survive and is actually manufactured to what we expected it to be. Then we did some what we call free-state Windtunnel test, that bucky in the bottom left corner with the rig at the back. So we did that before. We actually did a gliding test, and we did some design corrections after that. So we shortened the tail booms, we changed a bit of the empennage, and it was quite a successful visit from the German team. The next year, end of 2015, we had the American team out here, and they brought the whole embedded system, the autopilot, the camera gimbals, the propulsion. And so we did the whole integration process, and we did the testing on this, in this case, only on the free-state Windtunnel rig. So the whole integration process happened here. We did the integration, and it was a fairly successful test on the free-state Windtunnel. Then, I don't know if I can play this. Yes, so our most recent... Can it play? Our most recent attempt, it doesn't seem to be playing, a little bit. Our most recent attempt was to test the landing system that we've now integrated, and we wanted to get some flight mechanics from, some information from the actual drone. So we had the drone fitted with all kinds of sensors. We changed the free-state Windtunnel to be able to launch from it while we're still developing the catapult launch system. And we did a dummy launch with another aircraft, but before we could get the orange in the air, we actually broke the free-state Windtunnel. So it's currently under repairs. The next flight is scheduled for the second week in July. So hopefully by then we'll finally get this fat bird off into the air. Yeah, so this is just the schedule for us at the moment. We have our flight test scheduled for the second week in July. We're hoping to have the catapult launch testing by the end of September, October. And then the students for this year will start handing over by October, end of October, to the new team. And then we'll follow on to do more gimbal stabilization. We'll integrate the parachute system and so forth. So there's a lot of continuation on smaller little projects. It's quite an intense project, and we've had immense support from industry. So I have to really, there's so many people that I have to thank. John Monk and their team from the CSIR, Marius and Evangelos from Paramount, Adam from AMS, and Dave from the Epsilon group. They have been incredibly supportive on all levels, on mentoring, on guiding the students, on helping us with safety test cases and paperwork that none of us love doing in academia. Yeah, so they've been incredibly supportive in terms of getting the students to really understand what's going on and make this project quite a big success in terms of their education. So I really am appreciative, and we really can't function without the support from industry. Yeah, so I think that's it for me. That should give you a fair overview of what we're doing.